Hello, my friends from all over the world. It's my great honor and pleasure to be here sharing our ideas with you. We're Yiping Chen and Koyan Zhang from Department of Mechanical Engineering, National Taiwan University. As shown in our topic, in this work we want to discuss about how to generate excitation parameters through optimization, and further on, make a better estimation on model parameters. Let's get started. In this work, we propose a process for calibrating the unknown model parameters and validating simulation models, which include variance analysis, operation design, and parameter estimation. In today's presentation, I will demonstrate how to implement this process in a simple engineering case. First, we have to define our system's operation mechanism. In this work, we built an X-by-wire tricycle as a cheaper and more transparent testbed, which contains fewer physical models and unknown parameters. By assuming the only difference between simulation model and the real system is the model parameters deviation, and all the actuators are well identified, we build a corresponding physical model in Simulink. Also, path-following algorithm is used to generate operation commands. So, to describe the operation mechanism of these systems, we use a simple math function. X here represents how the model is operated, such as steering and driving commands in time series. Theta here is the model parameters, such as mass, inertia, and Y is the dynamic output, such as position and velocity in time function as well. Model parameters here represent the unknown parameters that are immeasurable or can only be obtained by inference. In our work, as you can see in this table, 6 important model parameters are chosen by engineering intuition that might needed to be estimated, including inertial, stiffness coefficients, and empirical parameters in tire models. Operation parameters determines how to operate the systems. In this case, X are the geometric parameters of the given trajectory for path following. Once the trajectory is defined by the operation parameters, operation commands for driving and steering can be generated by path-following algorithm, and simulation-based global sensitivity analysis for model parameters can be achieved by using the same operation commands. 4 operations are chosen in our work. Each operation is defined by 2 operation parameters. Here we quickly show you some of the trajectories that are formed by different operation parameters from the top view. Now we know what operation and model parameters are. Back to our goal in this research, we want to design operation that can excite specific model parameters, which not only have large main effect, but also small interaction effect. In our math representation, the optimal operation is defined as the upper equation. To realize the partial derivative through optimization algorithm, we built an objective function that is formed by total variance along with main and total sensitivity indexes, which are obtained from Sable's global sensitivity analysis method. As you can see from this objective function, the total variance will be maximized while the interaction effect of observed target and the main effect of the non-observed terms will be minimized. We believe under these circumstances, the identifiability of the observed target may be enlarged. For the 4 operations we've mentioned before, the optimum of exciting each unknown parameters are calculated. From all of the results, we picked a combination that can excite all the unknown parameters and generate a composite driving maneuver, as you can see here. It is expected that once we drive this vehicle by following this trajectory, most of our unknown parameters are participated in and its deviation are able to be observed. With the excitation operation ready, we use polynomial chaos-based common filter as the tool to estimate multiple parameters at the same time. Virtual experiment is said to replace real experiment to verify the proposed method because we can assume that the correct value of our model parameters is known. In this experiment, 5 state output is observed in our common filter. As you can see from the estimate result, we can have good estimates from theta 1 to theta 3. Also, theta 4 with smaller confidence, theta 5 with a deviation offset and not able to identify correct value of theta 6. To validate these estimate results, we substitute the estimate back into the model and compare with the result from virtual experiment in another independent operation, and use hypothesis testing to test if 5 observed dynamic output with the overall output can be seen as the same output performance where measurement noise exists. As a result, we obtain the equivalent test statistic equals 0.7725, which is less than 0.975. This means with 95% confidence, we can say that the estimate model parameters are identical to those of the real models. Concluding above, we show the implementation of our proposed method. The novelty of our work is to assign operation parameters as the design variables and generate excitation operation with several global sensitivity analysis techniques. With this method, we are able to know if the testing operations are suitable and are able to design testing operations that can excite specific parameters and potentially decouple the effects. Also, this method provides a more accurate estimate on parameters with higher confidence and smaller deviation. As you can see, the comparison from this figure, which is considered as a multiple solution situation, we believe with design and composite maneuvers, this situation can be avoided. In the future, we will focus on building the multi-objective cost function rationally and verify this method not only by simulation but real experiments, and hope we can extend this concept to systems with higher complexity. We hope this brief introduction can inspire your future work, and we would be pleased if you can give us more advice and discuss with us. Thank you for your listening. We're Yiping Chen and Koyan Zhang from National Taiwan University.